All right, so let's jump into the FEM simulations. Before we do that, let's look at the why we are going to be setting it up the way that we are. So what we're looking at here is our max deflection calculations that we hopefully have looked at in dynamics or will be looking at in dynamics. And it's this equation down here. So it's WL to the third over 3EI. There's a reason for every single one of these variables here. So the W, of course, is the weight at the end. We're looking at a cantilevered beam here. That's what this calculation is for. It's the max deflection at the end of a cantilevered beam. So this line would be our beam, and this is going to be our wall. So there's a connection here, and then there's no connection on this side. There's a weight at the end, and it, of course, is going to be weighing down the bar. So that's what the W is. That's the weight at the end of the bar. We have a L, that's the length of the bar. And you see how important the length is. So length is to the third power. So if we really needed to, if the deflection was too much, the first thing we might want to look at, or the thing that would have the biggest impact, would be shortening this length. Then we have all that over 3EI. E is going to be our modulus of elasticity, or Young's modulus. That has to do with the type of material that we're using. Are we using steel? Are we using aluminum, plastic? So that is going to be the type of material. And you can see up here, so we're using steel. Steel generally is about 30 times 10 to the 6 psi for the modulus of elasticity. Here we are using this value because this value is coming straight from NX. And our goal here is to get our max deflection to match the value that we have here and the value that we have in NX, and with those values to match. So to make sure that we have the best chance of that, we're using the exact value that we get for the modulus of elasticity for steel from NX. And that's going to be this value. And then we have I. So I here is our moment of inertia. And a moment of inertia has to do with the resistance to bending, has to do with the shape of the material, the orientation that it's in respect to where the load is at. Different shapes have different moments of inertia. Right here, we have the rectangle and the circle. This is the cross-sectional area. So if we were to take this beam and slice it down the middle here, that's going to be this shape. Now, we are using IXX because we want the weight to essentially be up here. So the weight's coming down on this side. So we're looking at XX. We're looking along this horizontal axis right here. If the orientation was swapped and we had the weight coming in from this side, so if this whole rectangle was flipped on its side, it would have to be the IYY, and that would be significantly less. So we're using IX here, and so that's how we were calculating the moment of inertia. And that's what this calculation over here is for. So we're calculating the moment of inertia, which is going to be the IX. So that's B times H to the third over 12. And that's what, so this is the cool thing about Excel, or why being able to create spreadsheets is important, is that I can come in and I can say, okay, well, instead of a base of 1, now we have a base of 3. How is that going to affect our spreadsheet? And then come down here when I go to the I actually have it set up with a drop-down menu saying, please select from the IXX options above. And so we are either selecting between the circle or the rectangle. I'll choose the rectangle, and now we can see how changing that is going to affect our calculations. And that's what it takes to do the max deflection analysis here. So we have the weight at the end of the beam, length of the beam, the material that we're using, and then the shape of the beam itself. All those play a part in figuring out the deflection at the end. So at the end, this beam is deflecting 0.777 inches, which is it could be a lot depending on what you're trying to achieve. This is great. If we have a single cantilever beam, this works perfectly. But Of course, a lot of times we're looking at a more complex situation, and doing the hand calculations like this can be extremely complex and complicated. And so we actually want to be simplifying the process by using NX to help us with a lot of these calculations. And so what we're going to do is we're going to set up this exact same scenario in NX and see if we get the same answer. Now, before we do that, I just want to say real quick that this is a very, very, very basic introduction to this. We're going to do one type of simulation. There are a ton of different types of simulations in the CAD software, and we are only going to be looking at one specific type and only a very basic intro to that one specific type. So let's go ahead and get started. So we're going to open up NX, make sure that we are in Roll Advanced, and we'll go ahead and open up a new file. When we model in inches, we'll be saving this to really you want to save it to a folder because we're going to have a few files that are made. So we want to be saving this to a folder. The part name, so the one that we're doing in class, so the rectangle, is not the one that you're going to be turning in. You are going to create your own model in your own FEM simulation and be turning those in. So the one that we're doing in class is not the one to turn in. So I'm not going to name this the homework 21C that it's supposed to be. I'm just going to name this rectangle beam, and I'll save that to the folder. And then, of course, this is where we are going to create our beam. Now, really what we should do is create expressions for our values, and then we can quickly change that. That's a good thing to do so that you can change those quickly. I'm just going to sketch and create the dimensions as I go. I'm going to create this on the front plane. I'm doing a rectangle, and I'm going to do from the center. My base is 1 inch, and my height 2 inches. Sketch is fully defined. Cool. Hit finish. And then I'm going to extrude this 36 inches. So I've got my beam. We can come over here to application and do more and design. And it's going to create for us a new FEM simulation. We will take all the defaults here. We'll hit OK. We'll name this solution 1 is fine. Again, all of the defaults are good here. We'll hit create solution. Hit OK. And now we are in our simulation. And it's where we get to create our scenario, and then we can solve for our simulation. That's where we're going to get our values that we are looking for. And we can get a lot of information from this. So stress analysis, if you're looking at what material do I need to use for, like, senior project, great idea to have some FEAs, FEMs in here or in the project to show why you did what you did. So why did I choose this material over the other material? Well, here's my FEM to prove that, to back up that data, back up that whatever I said. So that's what we're going to show how to set up here. And we're just going to go through this. Again, this is a simple one. So let's think about what we've done so far as the calculations go. We have weight, length, Young's modulus, and then the moment of inertia. Moment of inertia is, again, the shape of our beam. We have already done that because we created a beam with these specifications, the base of 1 inch and a height of 2 inches. We have done the length because when we created the beam, we made it 36 inches. So we've got 36 inches here, and because of our moment of inertia, we have or because of the way that we created our shape, we have that moment of inertia here. The things that we need to do is we need to decide our weight, or we need to put in our weight at the end of the beam, and then also our Young's modulus, modulus of elasticity. This has to do with the type of material that we have. So let's address that first. We see up here that we've got assign materials. Top left corner, we've got assign materials. We can click on that. Need to select the body. Well, we only have one, and so we can choose that. And we have a ton of materials to choose from. This is where we want to actually make sure that we're choosing the material that we're going to be using, or the material that is being used in this particular scenario. And what we are using is steel. So we can come down here to steel, and we can hit OK. So now NX is viewing this solid body as being made out of steel. So it's got all this properties of steel associated to it. Now we need to apply the 3D mesh. And we're going to come here to 3D tetrahedral. Going to click on that. Again, we need to select the body that we want to create this mesh of. I'm going to choose the beam. And here is where we have control over the size of the individual tetrahedrals. So element size is the size of the tetrahedral. The smaller the size, the more accurate the results. Not to say that having a larger tetrahedral is going to not be accurate, but if we have a complex movements and there's all sorts of forces going all different ways, it's going to be better to have a smaller size tetrahedral. We do not need to be concerned about that in this scenario. We'll be fine with pretty much whatever we select. If we're not sure about the size, we can come over here to automatic element size, and NX is going to kind of figure it out on its own, and it's going to say, hey, your size should probably be about your tetrahedral should probably be about this size, which is a lot larger than what it was before. So the smaller the tetrahedral, like I said, the more accurate, the more precise, but the longer it takes to actually solve, and the more processing power it takes to actually set it up. And so we don't really want to be doing that. So we're going to hit the automatic element size, and we're going to take what NX says to do, and we can hit OK. And then watch what happens to our beam as it goes through this. So we now have this split up into tetrahedrals. And so this is how it's going to process this. So as weight is applied on one end, it'll be able to see how the forces are applied between these tetrahedrals, and it'll be able to see the movement along the beam, and it'll be able to solve all these equations way quicker than how we could. Under the loads and conditions, this is where we apply the situation of the beam as far as how it's connected to maybe other components or just in 3D space, and what loads we have. So let's go and do the constraint type. And we want a fixed constraint. Remember, this is a cantilevered beam, so it's going to be connected to the wall on one end. And so I'm going to select one end of our beam here, and I'll just hit OK. So that's going to fix it in 3D space. So now this is connected to some surface, and it's not going to move, or at least it should not move. And then on the other end, we have our load. And so I'm going to come here to load type, and we'll have a force. We have a bunch of different ways of calling out the force. We'll be in pounds. We're supposed to select the object. Let's select this other face. And then we can go to specify vector, and the vector that we want to specify is down. We want to go down in this direction here. Depending on how you set up your model, mine is the Z axis, but yours might not be. So I want it going down, -Z. We don't want it to be going in this orientation, coming down this way. That's going to give us that IYY moment of inertia. So that would be significantly higher moment or a significantly higher deflection because that's a weaker, the moment of inertia is weaker in this orientation. This orientation, it is higher. And this is the scenario that we're looking for. The force that we said was 1,000 pounds. We can say 1,000 pounds, and we can hit OK. And we have all these red arrows pointing down. The red arrows are the force showing the direction. And then we have it supported, fixed constraint over on this side of the beam. So we have it set up. Now if we go back to our formula, we've got the force, we've got the length, we've got the Young's modulus, we have the moment of inertia. We have everything that we need to solve this. So we can come here to solve. We'll hit OK. And then it's going to start solving everything. It'll pop up, the solution is complete. Do you want to view all messages now? I'm going to hit no, because I don't. And I'm going to just cancel and close out of all this stuff. Now in our simulation navigator, which is a new navigator we have over here on our tabs, we've got solution 1, which is the one that we are in. You can have multiple solutions. We can go and do this again, change the load, compare the two results. Yeah, there's lots of things that you can do. You can choose them to be in different windows, and maybe take a picture with the solution side by side. But to see the results, we want to come down to results. Just double clicked on that, and then we have the structural results here. And what we're looking for, and I just double clicked on these. Looking for the displacement. And so our results here, so this is the side that was fixed. This is the side that had the load on it. And we see our max deflection here, and that's what we're looking at. Displacement, the deflection is going to be the 0.776 inches. We had 0.777, which is 1 thou off. I'll take that. Probably just some rounding somewhere that happened. But the FEMs are cool, because if we wanted to see the stress that's developed in the material, we can see where it's developing, how much is developing. So we could say, oh, maybe steel isn't what we need. Maybe we need, some other material. So this stuff is really nice to have, and it's really easy to take a nice picture of this. Now, if you open up the folder that your parts are in, you see you have a whole bunch of parts that were created, which is why I wanted to make this folder. The parts that you want to turn in are the FEM, this one, and your part that you created. So they're both going to be, part files, but one will be an FEM, and one will just be the regular model that we've been looking at.